Thanks for joining me, everyone. The title of the talk is Immutable Music, or the Time-Traveling Sequencer, which is, a bit of a mysterious title, but I always like those old novels with two-part titles. It kind of makes it sound a bit grander. And I like stories with a journey, which I'll also try and emulate today. So we're not searching for kind of dragon-hoarded treasure. We're looking for more bug-free code and code that inspires musicians and ourselves to keep creating. And hopefully there'll be a demo at the end if I get a move on. So I'm sure you've guessed what the central themes of the talk are going to be, or maybe you read the blurb. I'm going to be talking about functional programming applied to music composition and algorithmic music. There won't be much talk about, hardcore functional concepts. This is not a lesson on monads or type theory or anything like that. I'm just interested in musical outcomes. How can this help us design better tools? So the main focus of the talk is going to be on pure functions and how they can be used productively to make musical devices. So by pure functions, I just mean functions that always return the same input for the same output. That means they can't depend on any external mutable state or internal mutable state. That includes, class member variables and things like that. The title of the talk suggests that I'll be talking a lot about immutable data, which was my original plan. But as I developed the talk, it just became more and more about pure functions. So if you want to ask me about that in questions or maybe collar me afterwards, I'll happily chew your ear off about immutable data because it's cool. So in terms of musical applications, we're going to be thinking about the good old standbys of electronic music like step sequencers, groove boxes, arpeggiators, all the exotic varieties of sequencers that we see out there today. I've always loved these kinds of devices ever since I started playing with electronic music because they let me explore musical ideas that I could never play by hand, and they encourage accidents that sound good because the search space is kind of restricted in some ways. Of course, these days we have MIDI effects which perform similar kinds of functions, and most of the physical devices we use are running code anyway, so hopefully the implementation ideas we'll explore are relevant for those as well. And we might think about generative and algorithmic music more broadly. The devices we know and love are just a kind of subset of the possibilities in that category. So this is a live coding app that I'm working on, which uses the architecture I'll describe. And we're going to iterate our way towards this architecture. And as we do so, we're going to keep a few properties in mind that we want from our system. So the first thing we want is stability. We want to modify the parameters of our sequence, or even maybe the structure of the entire sequencer while the playback's ongoing. We don't want to lose time. We don't want stuck notes. We might want to even replace all of our sequencer code during playback, and we want everything to keep working. And stability of that kind is nice because it means we're unlikely to have many bugs, but also it encourages creativity because if we aren't worried that our sequencer is going to get stuck into some weird state, we can just forget about that and be in the moment and create. And we can also build more complicated structures on top of these solid foundations. Another thing we want is composability. So we want to compose music, but we also want to compose our programs in a nice way. They're unlikely to be as beautiful as a good piece of music, but we can try. And we want to express concepts that musicians care about and separate them into sort of pluggable Lego bricks, things like rhythmic structure, harmony, concepts like legato or swing. We want to encode those in individual rules that aren't tangled up together. And we want to reorder them, delete them, and reuse them, and compose them into more complicated rules, which we give names. And the final and probably most curious property of our system is time travel, which is just a silly name that I've given to the ability to manipulate time in ways that were hard to do before. So, stretching timelines, compressing timelines, copying musical timelines, and playing them against each other to make, classical canons or interesting call and response patterns, or flipping whole timelines. Sorry for the cheesy animations. I've just been learning Keynote, and it's really fun. So these are the properties we're looking for, but I didn't really start out with these high-minded ideals. So as so often in programming, this journey began with a bug or kind of a collection of bugs. And I've seen similar bugs like this throughout my career. So let me show you a few examples. This bit's kind of it's like a resume combined with a bug report, which is quite often the same thing for programmers. This is a granular synthesizer I built several years ago. Most of you are probably familiar with the idea. You generate events, and each event triggers a playback of a sound file. And the events might be spaced apart in time, but they can overlap as well, depending on their duration. And they might have different properties, like the starting position in the sound, or their speed, which translates to pitch. So each of those kind of dots represents one of these events, and we can change the interval between them and some other things like that. Really fun concept to play with, and great for making ambient soundscapes and things like that. So this was my first project. Lots of things were tricky, about that, but one of the biggest sources of bugs was when I added a feature to synchronize those event start times to the host tempo. Because when you start playing with this, you immediately want to start trying out rhythmic ideas. And allowing users to modulate the interval between these synchronized events was just really painful. I got it wrong a lot of times. That's why I actually haven't shown the feature, because some of those bugs are still there, and it's kind of embarrassing. So here's another project I worked on. It's an MPE arpeggiator in an app called Noise. And it's a really huge amount of fun to use, one of my favorite features that I've ever worked on. I didn't write this code, but I did maintain it for some time. A little demo of that. So the expression from each finger is mapped onto the notes that are generated from that note. So yeah, this did throw up quite a lot of bugs in the process of development, and I still don't think we got it perfect. You probably heard there that as I modulated the interval time dynamically, things were a little bit weird, and then they would kind of resolve themselves. So this was a really, really complicated state machine inside there, with all the expression stuff feeding into it. It's quite hard to debug or add features to. And one final example, this is my favorite programming language called Superglider, and each of those objects beginning with a capital P are streams. So you call a method like next on them, and they give you a new value each time. So the pbind object there, that returns like an associative container, like a map or a dictionary, whatever you want to call it, and that represents an event. And there's a special key inside there, dur, which tells the stream how long to wait before calling next again on itself. And then each of the items inside the container, they're generated by calling next on a kind of inner stream. So really fun to play with and twiddle around. I don't know if anyone's tried any form of live coding, but this is a really good place to start Superglider. But you may notice that each time I'm reevaluating this code, something's going a little bit out of time there. So when I reevaluate the code, we swap out this generator, and the intermediate state, which decides how long to wait until the next call, is lost, and it goes out of time. So Superglider has ways around this. You can kind of wrap the stream in an object that swaps out the stream for a new one, just the right moment. It kind of quantizes those changes. But it would be nice if we didn't have to use workarounds like that. So what are the commonalities between these bugs, which I've seen there and in many other places in my career? Let's dive into some code and try and find out what the core problem is here. So most of the event generating systems I've worked on started out like this. You've probably seen, oh, by the way, with the code examples, there's no need to read every single line. Just, look at the function signatures, look at, is it a class with some state, or is it not? Things like that, just the overall structure. So you've probably seen a classic audio callback with this format, present in all the major APIs and wrappers like Juice. So I'm using an abstract object called event, but maybe MIDI messages or some other time-stamped event is what you need to make. And the host or OS calls this to get the next chunk of music. And everything's measured in samples, so to know what that means in terms of musical time, you need to get the sample rate and the host tempo. And you just use those to make a counter. So each callback we subtract from the counter, and when it reaches 0, which might be in the middle of a chunk somewhere, we emit an event. And that gives us a regular pulse in musical time. So let's keep going with this approach. Let's add a feature. We're going to add some swing. So a very simple form of swing is to say that every other event should be delayed by some amount. So we're going to add another counter. It's called the swing counter. And this basically flips between 0 and 1 every event. And we're going to use that to decide whether to adjust our main counter's starting value so that kind of alternately expands or contracts the spaces between the events. So, starting to get a little bit ugly here, but it works, or does it? So one of the challenges that we've set ourselves is that the user can change parameters like the event period dynamically, or maybe even modulate them with LFOs or something automatic like that. And the host tempo can change at any time. And the user can just move the host playhead to any random point as well. They might rewind or something. And if any of those things happen, then our counters are now in the wrong state. So they're going to keep happily counting down and start emitting events that are totally out of time with the new playhead or tempo. So please don't try and read this. We need some code to detect if any of those factors have changed, and we're going to recalculate the counters if they have. Speaking from experience, this isn't that reliable. Later on, more conditions that require a recalculation might come out of the woodwork, or if we start adding features, then it's going to get thorny in here. There's more things to reset, more counters to track. You can try encapsulating the concept of a counter into a class that helps you a bit. But it's always going to be an area of complexity, especially when the counters have dependencies on one another. So we're quickly heading towards a complicated state machine. And good luck unit testing this in a way that reflects real use. It's very hard to unit test this iterative system because you have to simulate whole sequences of time to find out if it keeps doing the right thing. So as you do, after a few projects that went this way, the next time I sat down to do it again, I kind of thought, why is this happening? Can I avoid this next time? And maybe after reading one too many evangelical functional programmers on Hacker News, I started thinking about these blasted counters. They were getting me down. So each time our function's called, it has different behavior based on these counters. And whether or not the counter's in a valid state relative to the rest of the system is expressed in a really error-prone way. In some ways, these counters are supposed to represent time, but they're not really doing a very good job of it. They're disconnected from the reality of musical time that we care about. So let's see if we can bring that notion into our system in a more robust way. So we were kind of pushed in this direction a bit by the classic audio callback function signature. It tells us basically nothing about the period of time we're supposed to be representing. It doesn't tell us when it starts or even how long it is in a way that's musically meaningful. And that's not really its fault. It was designed for audio effects, not sequences. But let's make a callback that matches our domain a little bit better. So we're just going to add arguments to the callback that tell us what time range it represents. And I'm using musical time instead of seconds here. It's just easier to do computations like that. Did anyone see the talk about units in C++ the other day? Yeah, really good talk, so I advise you to watch that. So for now, you can imagine this type measure is just an alias to a float or a double. But in reality, I'd recommend you create a richer type that helps you do musical operations. So while we're here and fiddling around with this, let's make our function return a new list of events instead of mutating an old one. So this will help us compose our functions in a nicer way, but I can imagine that the experienced audio programmers here are getting a bit worried, what about allocations, real-time safety, etc. well, let's just forget about that for now. Let's just see what this buys us in terms of code clarity and worry about efficiency later. So we might as well do this as well. Let's just package up a list of events with a time window. I called it context. You can probably almost certainly come up with a better name than that. This makes our composing our functions really clean and easy. So for me, when I look at this new function signature, it tempts me to implement that basic pulse example in a different way. So we've gotten rid of any counters. All we do is we figure out when is the next event falling in the requested time window, and then we're going to keep adding regular events to fill up the window. And of course, the tempo is irrelevant because we're using musical time. So it's the job of the caller to calculate the sample positions that those correspond to. So visualizing that, we ask for a time window, and it fills in the events for that time window. Great. We can ask for a different time window, and it fills in those events. And notice it only fills in events that begin inside the time window. That's a choice that I made, and it has some consequences later on, so I just wanted to draw your attention to that. And then after that, we can ask for the original time window again, no problem. So there's no reset code needed. If subsequent callbacks request drastically different time windows, it still gives us the right result. So with our original function signature, there wasn't really even a way to express this. All it says is give me the next chunk. This new signature is a contract that says the order of previous calls and whatever their inputs were doesn't matter. And that makes this unit test very easy, this function rather, very easy to unit test and very stable. Oops, I forgot about that bit. So let's have a look at how we can chain these together. So we create an empty context. We're looking for the events between bar 0 and bar 8 here. And we're going to place some events into it at 16th note intervals. And then we could set an amplitude property on the events, maybe in some pattern, which tells our playback system to play them louder or softer. And then we can set a frequency property according to some pattern as well. So maybe we're making an arpeggiation or something like that. So the functions compose nicely, but it's a shame we have to read them inside out. So of course we can quite easily just make these read a little bit more how we expect from top to bottom. And we can move our data into each function, which slightly mitigates some of the copies we might have to do otherwise. So let's keep going, and let's try and do our swing example in this format, because that was where things started to break apart a little bit before. And, it looks quite easy. It looks quite nice. We check all the events we've received, and for any that land on this kind of swung interval that we've decided, we delay them a bit. And, it looks nice. It looks clean. But unfortunately, this doesn't work. And it's a bit of a subtle reason. Can anyone guess why this doesn't work? Yes, it's basically that problem. It's worse than that. I'll visualize it and show you why. So as before, we're going to call our pulse, to create a steady pulse of events, and then we push them into the swing function, and that delays some of them in time. So at this point, an event's been moved out of the time window, but that's not actually a big problem because we can easily trim those away. That's very simple to do. The problem comes if we try a different window of time. So as before, we fill in the pulse, but we don't have an event in this position here because it starts before the window we asked for. So you see the problem now. When we give this to the swing processor, we'd expect it to have a note there, but it can't, move an event that it doesn't know about. It doesn't know this exists. And that's really bad news because we're going to get inconsistent results depending on the boundaries of the windows that we're asking for. And any function that wants to move notes around in time is going to suffer from some variant of this problem. Yeah, silly animations again. So what we really need to do is kind of somehow communicate to the source, that's the pulse in this case, that we want a slightly wider window so that we can check, are there any events just before that might need to move into my window? Too many animations, and then we return a nice consistent set of events. So we need some form of inversion of control. And Another way of saying this is the Hollywood principle. Don't call us, we'll call you. So at the moment, we're calling the pulse processor, and then we feed the result into the swing processor. But what we kind of need to do is to go the other way. We need to pull through this system. So we need to ask the swing processor, what have you got for me? And then that asks the pulse processor, what have you got for me? And at that point there's a chance for the swing processor to widen or narrow this window. And we might end up doing big chains of these as well. So this is one way to fix the problem. It's the first way I came up with, although I changed this later. So we're going to make a linked list of functions. And we call the first function in that list, which is actually our last processor, the end, and we call it with an empty context. And then this function can call its source to find out what it should operate on. And that's where it has this opportunity to expand or contract or move the window of time. And remember, each function must give the right result for any window of time, past or future. So it's perfectly okay to do this. So one more visualization, because once we've done this, we've actually kind of found time travel. We've accidentally stumbled across a new feature. So we're going to ask the swing, that's the top processor, or the end, for the events between bar 0 and 1, and it can ask its source for a wider window. So it can make sure that it can move those events over the boundary if it needs to. And then let's imagine its source is a fictitious processor called leading note. And what this does is, when it sees a note or an event, it makes a copy and shifts that copy earlier in time. So we turn like da, da into da, 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 da. So this processor has the same problem as swing, but in the opposite direction. If an event should land just after the boundary, then it would fail to see it and copy it back in. So it's going to do the opposite. It's going to ask its source about the future. So of course this isn't the actual future, because in the meantime the user might change a parameter or stop the playhead or blow up their computer or whatever. But it's like the future in this immutable timeline that's described by our list of functions. So this is time travel essentially, and no need for flux capacitors or plutonium. So now we've got this, we can start doing more interesting things. We can imagine a function called speed, which gathers a wider window from its source than we asked for, and it squeezes all the events it finds in there together. Or you might have one that does the opposite, asks for a narrow time window and stretches them apart. So you can think of this like the stars in space, which move apart. They're not necessarily in motion, but the space in between them is actually expanding. So here we can expand or contract whole timelines. So there's a couple more things. We're getting close to the architecture that we want now. There's just a couple more problems I want to solve to make this into a useful system. They're quite easy to fix, actually. So we've got a lot of very specific functions like this, which, it's not very dynamic. And we don't want to write another version of this function for eighth notes or quarter notes. We could introduce mutable state again. We could turn this back into a class with a member variable. But, we're trying to get away from that. At that point, we're, back in that land where it's hard to unit test. There is an alternative. So let's take advantage of our system's stability and just compute a different version of this function. So this is a very common pattern in functional languages. It's called closures, closure with a S. So you could think of it like a function factory, and we call a function that returns a function with the signature we want. And we capture some state into that return function that gives it different behavior. And because of our system's stability, we can just swap out the old version of the function with a new one at runtime, and everything stays consistent. So this is the main method of abstraction in my sequencer project. The second problem you might have anticipated is introducing random values. So they're tremendously useful for creating variation, but pure functions can't use pseudo-random generators in the normal way we use them. because they're essentially mutating a value. You give it a seed and then it mutates that value each time you call it. So quite an easy solution here. We just use a hash of the event to kind of create something that looks random, appears random to the user. But in actual fact, this is going to return the same output for the same input every time. Because our system would be inconsistent if it doesn't do that. Imagining in the time travel scenario, if you're using a normal pseudo-random value, you might look ahead into the future and say, is there going to be a note there or an event? And it says, yep, there is definitely. So you do something, and then when it arrives there, you'd get, maybe it doesn't produce an event, and you've got an inconsistency there. So every time we play our piece, we're going to get the same random values in the same positions, which, in my opinion, is actually a really nice property because it makes your piece, as a composer, it makes your piece feel consistent. You're always going to get the same sort of pseudo-random sequence. And if you want to change that sequence or have a different, if you're not happy with it, you could always add an extra kind of constant to the hash value if you want a different seed. So I was going to ask some questions at this point because I'm going to move on to a demo in a moment. I might as well do that. I'm ahead of time. I'm talking quicker than I planned to. So while the code's fresh in your mind, does anyone have questions about the approach, limitations or things like that?
Considering that you're using
Mike.
Considering that you're iterating through like vectors and arrays and stuff, so at this point you cannot change the sequence during the reproduction. I mean, like you're using an iterator, they get invalid to the point that you alter the sequence.
Well, I'm copying the sequence every time at this point.
Because that's the whole immutable point.
Yeah,
okay.
Or copying or moving. It's okay to move your sequence in there as well. So yeah, I mean, this is where, the reality of audio development, people, if you're doing this on a real-time thread, then you're potentially allocating when you push new events in there. So you just have to come up, because I want all these nice features or this nice way of working, you have to come up with solutions to that somehow. So maybe you have, object pools or things like that, pre-allocated buffers of things.
So you still have a state in what you're which is the event, the end of your event. So for example, if you scale down or scale up the speed, the end of the event also moves.
Yes, that's right. Yeah. So I haven't talked about the length of these events. The other thing that I mentioned at the start was stuck notes. So the way I solved that the first time round was to essentially have a queue of note offs. So whenever we trigger a note on, then we also push a note off into the queue, and it will always get processed, which means if I swap out the sequencer or swap out something, then there will definitely be a note off for every note on. So once you've got that queue, you can kind of, if you need to, you can kind of tag those note off events and like move them around if you find that something is going to change. But I haven't really come up with like a perfect solution for that. That's where things get a bit error prone again.
So if the note off was becoming an event by itself, so instead of having...
Yeah. So a system that's very similar to this, I kind of discovered how similar it was halfway through working on this, is tidal cycles. And I think that tidal cycles has event starts and event ends separately. So in that case, if you look at a window, you might have half a note in that window. So you can treat them the same, and then you'd have things like expansion of the notes if you stretch time. So I had to slightly hack that into my system. It's not, is it a hack? I don't know. It feels less elegant, perhaps, because when I stretch the timeline, I have to also look for the length of the event and stretch that also.
Thanks.
I was just wondering, when you went from the stateful implementation to the functional one, was that like a rewrite, or did you sort of iterate your way there?
this was like a fresh project. So I started playing with toy implementations of the old way I was doing it and trying different ideas and this is what led me. So I actually experienced that thing where I wrote had this nice functional thing, and then I wrote something that moved events in time, and I realized that why this wouldn't work. So then I had to figure out this idea of widening and moving event windows. So it was an iterative process, but informed by experience.
In the beginning, when you when you realized, okay, there is a point of time that I'm not observing and there might be a node starting, you decided to open up the time window that you observe. But by how much would you open that window? And it feels like an arbitrary decision that you made. I'm looking into that. So you're just delaying the problem, don't you?
Well, it depends. So that depends on what you want to do. So some things like swing, if my swing has certain properties, I know that it can only move events so far. So I only have to expand the time window by that much. The same thing with a leading note. If I'm leading notes of eighths, I only have to look 1/8 note into the future.
So the expansion is a trait of your swing processor.
That's right. But there are things you might want to do where you soon discover that you can't work it out without knowing the entire history. And so there are limitations to this, by the way. I don't want to pretend that this is like a perfect system. There are some inherently iterative things that you want to do. So for example, if we're creating events that are randomly spaced in time, and then we want to arpeggiate those events, we have at any given chunk in time, we have no way of knowing like where we are in the history of events. We don't know how many precede where we are now. So again, this is where things become a little bit less elegant. You have choices. You can try and decorate your functions with some extra metadata, for example, that says, hey, I repeat this often. So then I know that as something that needs to know where I am in an iterative position, I can say, okay, you repeat this often, so I only need to check back that much. Or another option is to have, in the same way that you can call a pure function from an impure function, but you can't call an impure function from a pure one, you can have a pure functional sequence, structure going on up here, and then at the end you can do some iterative things or some stateful things. So you can kind of cordon off the tricky parts. So, any more questions? Yeah. I've still got, I think, 10 minutes, so that's good, because I'm hopefully going to do a demo of the system I'm working on.
More or less a follow-up to...
15, okay.
Okay, follow-up to that one. In functional programming languages, it's quite common that you have like infinite sequences. Have you thought about that? Like just natural numbers and then take 10?
Yeah, so obviously in languages like Haskell, they have lazy sequences, which kind of can be infinite. It's interesting because you could think of these functions as a kind of a lazy sequence or an infinite sequence, and then we can just, but unlike those lazy sequences where you have to start at the beginning and keep asking for more pieces, in this you can jump to any point you want and ask for any area. So it feels almost like a data structure where you can index into it at any point, and it can be an infinite data structure. Any more? So maybe, I don't know, I'm way ahead of time, so I talked quickly. So maybe I'll do a demo, and if anyone has further questions from the specifics of the demo, I'll try and show you. So yeah, the system I'm working on is a kind of live coding platform, and it uses almost exactly the architecture I've just described, but it's not written in C++. It's written in Scheme, which is a dialect, a kind of Lispy dialect. And it's a really good language for the dynamic redefinition of functions, and it has really nice meta-programming capabilities, which are great for DSLs. So just brace yourself for lots of parentheses. I love them, but they're definitely a Marmite kind of thing. Right. Let's get this up. I think I have to mirror. Okay. Right. So this is the system I'm working on, and the playhead's always running. I can pause it, but I just don't have nice buttons for that yet. So let's write a pattern and call it ADC. So this is a function. It's a function call. So if I evaluate just that thing there, it tells me it's a procedure. That's what Scheme calls functions. And then so that's what this is, this thing. So you're allowed, because of the really simple semantics, you're allowed to put symbols and weird things into your function names, which also helps with creating musical DSLs. And I can call that function, and it gives me another function. So it says node chains, you can see that. So this is the thing that implements those linked lists of functions that I mentioned before. So let's make some events. So first, simplest thing we can do. So it's creating blank events. Well, not quite blank. It has a scale degree. I should. But, screen's small, so this is a quick little alias for that. So can I go a bit smaller? Can you guys see if I do that? Just give myself a bit more room, and let's do this. So we can spread some events over time. Right? And we can subdivide these things as well. So we can say, but let's keep it simple for now. And let's also change the instrument, because it doesn't have any information telling it what to play, so it just plays a sine wave. Let's play something called Pulse Luck, and give it a little bit. Whoops, what have I done? Oh yes, that's right. I changed the syntax, so I forget how to use it. Okay, so let's have a go at some time travel. So this is a time travel operator. So if I... Oh, my goodness. Oh, yeah. Live demos, right? Don't try. So this is doing what I talked about before. It's a bit like that speed or slow thing. So I can multiply time, the whole timeline, and get... So each time I evaluate this thing, I'm swapping out an entire tree of functions, and the playhead just keeps going. Everything, I can just delete everything, and it's all still consistent. So what if I make this a negative number? Can anyone guess what will happen? Shouldn't be too hard. Yeah, it'll be reversed, because we'll be fetching events from the negative mirror of around 0, and we'll bring them and flip them around into the... Right, okay, so not too interesting yet. Let's do this. So what this is going to do is it's going in different segments of the real timeline. It's going to have chunks of a sped up or slowed down timeline. This is confusing me. These damn parentheses. Okay, so this is nice, but I said that we can also copy timelines and play them against each other. So that's what this operator here does. Each arm of this operator is a separate copy. So if we go, we've got the original played against this kind of tweaked one. So we can also we can apply other changes to these. write fractions as literals, which is really, really nice for music. So we can keep changing things. Let's go. Oops. We can, we can keep doing. Do stuff like that. So this app has these like Ableton-like clips here are just files containing text. So what you're looking at here is a really big tree of pure functions. So don't tell me that pure functions can't do cool things anymore. Let's try something a bit like that leading note thing I mentioned before. So this thing is called taps. It's like a delay. Right? And let's just make the delayed copies a different octave so we can hear it. So this delay also works in reverse. Add some randomness to this. So this question mark is just a function call. So we're going to change that. So let's try something more interesting. Let's not do these together. Okay. So let's simplify things and make one more copy of this thing that we're doing here. And here we're going to let's slow it down and let's change the instrument to phase tries. Okay, and let's use an operator called chord. Operators that I'm using here are fairly low level. I'm just kind of in the process of building more high level ideas on top of the low level ones. So, there's a long way to go, but hopefully that gives you some idea of what we can do. The idea is for this to become like a fully featured live coding app that you can play with functions basically. So let me just turn off bits selectively. So I think there's still a couple more minutes left for questions. If anyone has any questions about this thing, or there's one over there.
So I guess you're using as a sound processing engine. You use Super Collider underneath. Or?
That's right. Yes. Yeah.
Oh, okay, cool.
Yeah. So Super Collider, for those who don't know, is actually two things. It's a sound synthesis server that's written in C++ or C, with a kind of interpreted language that communicates via OSC. So you can just hijack that and send your own OSC. So that's what this is doing. You can actually send and define whole synthesis graphs or templates for synthesizers and send them across, and then instantiate voices of those. Yeah.
So the process would be to first design your synth in Super Collider and then like sequence them?
So luckily there's a Scheme project called SC3, or no, RSC3, which has, so it actually lets you do that in Scheme. So it generates the right OSC commands. So this is a Scheme function that sends something to Super Collider, sends a synthesis template, for making.
Yeah, that's super convenient.
Yeah, it is convenient, isn't it? Yeah, I mean they get a bit ugly. I think I need to write some macros or something horrible like that to make it nicer. But yeah, it's really convenient. You can redefine these as you work as well.
Thank you.
Thanks. So I think it goes without saying that I find this extremely, extremely nice. Have you thought about, or are you planning to implement like something like serendipity?
That's a great question.
And if so, how?
Yeah, so it's something that feels, because of like this idea that everything's preordained, when you write a function, then the whole history and future of that function is preordained. It feels like serendipity might be a bit missing. But we've got random operators, so we can randomly choose functions as well if we want. I think you can get a pretty long way with doing something like that. So at the moment, my random operator just generates random values, but it would be really cool to say, like, every bar choose one of these functions, and that function could be a whole big tree that, So again, I haven't really got to the point of, it hasn't got very nice tools for high-level music composition where you can actually, make arrangements. But having that would be a good step so that you can make random arrangements. Yeah, it's a good question though, because this kind of immutability kind of makes you feel like things aren't going to be flexible or dynamic or something. Yeah. Any more?
I don't think you said. Does it have a name?
Oh no, it doesn't. I can't come up with one. And every time I do think of one, I start hating it after a few days. Luckily, it's ages away from being releasable. This is very much a research project at the moment, so I've got time to figure that out.
That would have been my next question. Where and when can we download it?
Yeah, not too long, hopefully. The idea is, all this scheme code, my plan basically is to make the scheme code open source, but this kind of editor that I'm working on, a paid for thing to make some money off it. To me, that seems like the best separation between openness and money. Oh, there's one behind you.
Hey, have you got any plans to make it networked at all, like Jibber or something like that?
It's a good question. So because of the OSC, the kind of Super Collider server thing I mentioned before, people are already, and have been for years, doing really cool things with networked Super Collider setups. That would be really cool. Another nice thing is that, serializing a piece of music here is for free. It's just some text. So it might be cool to have some network ability to just throw those across. You could probably do like a really bad version of that with AirDrop right now, just AirDrop text files. But if a nicer ergonomic version of that would be really fun to try. And also Ableton Link is something that I'm looking into because, it's so good. Ableton Link, it's changed my life. Yeah, so I need that.
Cool. I'm afraid that's all we've got time for, so thank you very much, Tom.